Thank you, Leon. I'm AJ. Today I'll be talking to you about a project on programmable lithography mask. This project is done by Mantel and me in Professor Geoffrey's group at MIT. As you all know, electronic devices are used everywhere and they're being used every minute of our life. One common thing is that they all contain chips with submicron or micron-sized devices. And to make these devices, we rely on a patterning technique called lithography. To understand lithography, all you need to do is look at this image. For lithography, you need a mask. You lay the mask on top of the substrate. And in this example, if you spray paint the mask, the pattern of the mask will be transferred to the substrate. In semiconductor industry, lithography works in very similar way. In this case, you have a mask, a substrate, and on top of the substrate, you coat it with a layer of polymer. When you shine light onto the polymer through the mask, regions of the polymer which are exposed to light gets washed away. In the next step, if you deposit materials onto your substrate, materials are only deposited in the regions of the polymer which has been washed away. And that's how pattern transfer works in lithography in the semiconductor industry. The problem with lithography is masks are really expensive. For 14 nanometer nodes devices, you need more than 50 masks per set, and you need it every time you come up with a new design. Each set can cost up to $1 million, and the lead time can be at least a few weeks. So it will be really desirable if we have a dynamic patterning method where we can generate new patterns on the go. In today's day, dynamic patterning is primarily achieved using maskless lithography. There are two classes of maskless lithography. There's the raster method and the projection method. One example of raster method is E-beam lithography. In this case, you have an electron source which you raster across the substrate. You can think of it like using a pencil and writing on a paper. One example of projection method is digital light processing lithography, or DLP. In this case, you have millions of microscopic mirrors that divert and project light onto your substrate. For regions where you don't want to be exposed to light, you simply adjust these microscopic mirrors. For E-beam lithography, the resolution is really good, but the writing speed is very slow. For DLP lithography, the writing speed is much faster, but the resolution is poor. So there has always been a consistent trade-off between speed and resolution. The goal of our project is to come up with a dynamic patterning method which have very fast speed and very high resolution. Our project started out with looking at cells with tunable optical transmission. Our cells are very simple. It consists of two metallic layers sandwiching an oxide barrier. When you apply a voltage across this cell, you can toggle it between a transparent and opaque state. Due to the simplicity of the cell, we have very high pixel density, very fast response, and it can be fabricated at very low cost. If you arrange these cells in a crossbar array which are tightly packed, you can make a programmable mask. So this is very similar to the displays in your house where you have millions of pixels. And in our case, the pixel is 50 micron by 50 micron for our first prototype. So now I will show you the results of optical lithography done using our programmable mask. I will show you images of photoresist pattern that remains after we have done lithography using our mask. So here's an image of the photoresist that remains on the substrate after doing lithography using our mask. And in this case, all the pixels are turned off. By turning off, I mean that all the pixels are being set to an opaque state so that it blocks light. In this case, you can clearly see that photoresist remains on all regions of the substrate. In the next step, we program it to generate a pattern with the letters MIT. And in this case, you can clearly see the photoresist pattern having the letters MIT with an exclamation mark. So you can read the letters by looking at the bright regions. So for our next prototype, we will be shrinking the dimension of the pixel down to 200 nanometer. And for our third prototype, we aim to be more aggressive, down to less than 100 nanometer. In terms of benefit, we have a programmable mask with very fast programming speed and also very high resolution. For our end market, we can target not just prototyping, but also volume production applications. The reason for this is we have a wide area mask, and all you need to do is program it once for a new design, and then you can use it as a stepper. In terms of entry point, we plan to target R&D labs first, specifically labs in academic institutions. We can either make a programmable mask that can slot into current mask aligners, or we can build a tabletop lithography system. We believe we are the only ones who will be able to make a cheap lithography system which have resolution down to 100 nanometer. So I'd like to acknowledge our catalyst, Sanjay, who has been very helpful throughout the years. I also like to thank Paul, who has given us a lot of useful advice. I'd like to thank the team, Mantau, Jeff, MIT Materials Research Lab, and most importantly, Deshpande, for supporting us throughout the years. So for my last slide, I'd like to mention that I appreciate any connections to design engineers in the semiconductor industry or people who work in foundries. Thank you.